Hello and welcome back to Educator.com and welcome back to physical chemistry. So last lesson we introduced statistical thermodynamics and we gave you a broad overview of what our intent was. So today we're going to continue discussing this statistical thermodynamics and we're going to introduce the various partition functions. Okay, so let's jump right on in. So we said, let me see, should I work in blue or black? I think today I'm going to work in black. Okay, so we said Q was equal to 1 over n factor, well, let me write it this way. Let me write it as q to the n power divided by n factorial, where q, the molecular partition function, the molecular partition function is Q is equal to the sum over the I states of the G sub I times E raised to the E sub I over K times T. Let me make my K a little bit better here. So K times T. So in this particular case, I is the quantum level, G sub I, that's the degeneracy of that level. The degeneracy of the ith level. And E sub I, that's the energy of the ith level. Energy of the ith level. Okay. In this lesson, we seek expressions for the Q, the molecular partition function for the Q of various systems. In particular, we seek Q of translation, which is going to be symbolized as QT. We seek the Q of vibration, the molecular, so the translational partition function, the vibrational partition function. This is going to be Q sub V. We seek the rotational partition function, which we'll symbolize with Q sub R, and we seek the electronic partition function, Q electronic, which we will usually symbolize with Q sub E. Occasionally we'll use Q vib, Q rot, things like that. Okay, in these lessons, in this particular lesson, we limit ourselves to monoatomic and diatomic gases. Atomic gases. Okay, so each particle of an n-particle system has energy E. Well, the energy of the particle is distributed among the different ways that the energy can be stored. The energy is equal to the particle has translational energy, the energy of its motion. It has vibrational energy, in the case of a diatomic molecule, how much it's vibrating. It has rotational energy, if it's diatomic molecule or polyatomic, it's rotating. And it has electronic energy. How much energy is just by virtue of the electrons in that system. Now, since E is the sum of four energies, the translational, vibrational, rotational, and electronic, the molecular partition function is the product. That's how it works, is the product of the individual partition functions. The partition function for translation, the partition function for vibration, the partition function for rotation, and the partition function for energy. The energy is the sum of four energies. The molecular partition function, the total molecular partition function of the molecule, is the product of the individual partition functions for each component of the energy. In other words, Q is equal to Q of translation times Q of vibration times Q of rotation times Q electronic. Okay, we're going to begin with monoatomic ideal gases. So we begin with monoatomic ideal gases. Energy equals energy of translation plus energy of electronic. Okay, the reason is an atom does not rotate. So the energy of an atom consists of only two components. It has the translational energy, its energy of motion, and the electronic energy. An atom does not rotate, and an atom does not vibrate. Does not rotate, nor does it vibrate. So the energy of the atom is made of translation and electronic energies. That's it. When we deal with a diatomic molecule, it's going to have all four.